So, you remember this was number 22. This was where I was talking about putting in this big lambda term. I said that the big lambda term is because you really do have first nearest neighbor short range ordering. The A's tend to prefer to be next to X's, the B's want to be next to the Y's. So we replace XAXX by the number of probability of a first nearest neighbor pair, which is XAXX plus Y, and the probability of an AY pair is XAXY minus Y, etc. We do this. Then this was the quasi-chemical model. We distribute the pairs. We distribute these pairs over the pair sites, divide by the number of pairs in an ideal solution, and add on the ideal entropy. Right, we talked about that. So this is the modified quasi-chemical model taking into account short-range ordering. Here I did it with a variational parameter XAXX plus Y, and then I set dg/dy to be 0, and what you get is you get an equilibrium constant for the exchange reaction, and it tells you how much the short-range order is shifted. Just the notation, this is just a change in notation. Rather than writing XAXX plus Y, that's the probability of an AX pair, or in the quasi-chemical notation, XAX plus Y is the mole fraction of AX pairs. These are the pair fractions. Okay, so this is just exactly the same thing as here, but instead of writing product XAXX plus Y, I write the pair fractions, and this is the pair fractions of AY pairs, the pair fractions of BX pairs. Okay, so in the quasi-chemical model, we're replacing XAXX by the pair fraction. We're replacing XAXY by the pair fraction. The entropy, again, here, the XAXX plus Y is the pair fraction, so we're distributing the pairs, XAXX log XAX plus XBXX log XBXX over the pair sites. This overcounts the distribution. We divide by the probability of an AX pair, and an ideal solution is XAXX, add back on the ideal entropy, and so this is just what I said before. Then you end up with this. Now you don't have to solve this. As I said, this equation here then, in the polynomial model, this equation is solved approximately by expanding the log y as a first order Taylor expansion, and we end up with then this big lambda term. But you don't have to. Lander did that because he didn't have all the computers and everything. So you don't have to do that. You can solve this equation or this equation here, which is now this equilibrium constant becomes x of AX pairs times x of BY pairs. You solve the thing numerically, and then you don't have to make the Taylor expansion mathematical approximation. And this is in fact what the modified quasi-chemical model, first nearest neighbor short range order does. You simply are replacing, you're simply taking into account the fact that you can have short range ordering by ordering of first nearest neighbor pairs, and then you solve the whole thing, find out how far this thing is shifted, etc. All right, so that's the first nearest neighbor. And this is the same, now this was for the monovalent things, but if you are doing what I just said about the equivalent fractions, then you just do the same thing, you replace all these by equivalent fractions, this becomes G prime, it all comes out to be the same thing. I'll give you the final paper to read over because the mathematics starts to get a bit hairy, but the point is we solve this thing correctly, and it's a first nearest neighbor quasi-chemical model. We're considering, it's quasi-chemical model, we're considering pair bonds, AX, first nearest neighbor pair bonds. The entropy is an approximate expression given by distributing the pairs over pair sites and then making this correction just as we did in the one sublattice model. You overcount the number of pairs, so because an AX pair here, you can't have a BY pair there, so you make this approximate correction. And okay, as I said, when you do this, you then bring down your miscibility gap. Your miscibility gap when the complete ionic and the complete random mixing model was too big, and now you bring down the miscibility gap, but you overdo it. Okay, so solving this thing exactly is equivalent to the big lambda term. I'm very sorry I'm wrong here because there is no lambda term there. This comes out. All right, now the problem then, as I said though, when you do that, that is just exactly the same as this, except wherever I put XAX plus Y, which is the probability of an AX pair, you just write XAX. The quasi-chemical model just solves this, and does it correctly without doing the Taylor expansion. That's all. But for small values of delta G exchange, it comes up to almost exactly the same thing as the blender model with the big lambda, because the mixing is almost ideal anyway. But as the delta G exchange becomes bigger, then it's better to solve the equation correctly rather than use the Taylor expansion approximation. But you still get the problem with, as I said, if the experimental shows a miscibility gap along this diagonal, if you do this thing here, you end up with basically okay at the end, but you get too negative in the middle. This is overdoing it. Okay, so what's the problem? And the problem was identified basically as followed by one of my students, Yves Dessereau, a long time ago. And that's the following. Let's consider this system here, and let's say this is your stable diagonal, so that for this is AY plus BX gives you AX plus BY. The delta G exchange is negative, so this is your stable pair. So your short range ordering, when you solve this thing, then your quasi-chemical model, your short range ordering is going to displace this reaction to the right. So you're going to have a preponderance of AX and BY pairs and not that many AY and BX pairs. The bigger is delta G exchange, the further this reaction is shifted to the right. Okay, your equilibrium constant shifts it to the right. So if you have a fairly negative delta G exchange, when you're down in the middle here, you're going to have mainly AX nearest neighbors and mainly BY nearest neighbors. Short range, first nearest neighbor, short range ordering. Now, look at the binary system here, AX, BX. In this binary system, you have an excess Gibbs energy, which is given by alpha of ABX times YA, YB, a regular solution type term. Okay, now remember this regular solution type term, this is second nearest neighbor interactions. And here this alpha ABX is approximately given by n naught Z over 2 times the energy of an AB second nearest neighbor bond separated by an X minus the energy of the AA and the BB bonds. This is your standard regular solution theory. The alpha, the reason you have this GXS, or the alpha is not 0, is because the AB second nearest neighbor bonds are, let's say, weaker or stronger than the AA and the BB bonds. So this is just your second nearest neighbor regular solution term. Okay. So what this means is that if I mix AX and BX, if I take AX and BX and I make a mixture in the binary system, I'm forming AB bonds, which are, let's say they're stronger than the AA and BB second nearest neighbor bonds, so this whole term becomes negative. The whole standard regular solution theory. If I mix AX and BX, AX contains only AA second nearest neighbor bonds, BX contains only BB second nearest neighbor. Wait a minute. There should be a B over here. There should be a BB bond. Okay, so when I mix regular solution theory, when you mix AX and BX, what you're doing is you're mixing A and B on the same sublattice. First nearest neighbors don't change, it's only the second nearest neighbors that change. And here you have only AA second nearest neighbors, here you have only BB second nearest neighbors. When you mix them, you're forming AB second nearest neighbors, which are stronger, so that gives you a negative term. All right, and then when we go into the ternary system, we multiply this whole thing by YX. Okay, but when we get into the ternary system, let's say we're now going into the ternary system, so we're taking this term here, we're multiplying it by YX, and we're going into the ternary system. So in the ternary system, we have a term. In the ternary system, one of these second nearest neighbor terms is going to be that. Now, in most of these salt systems, as I showed you in all those systems with alkali chloride, cobalt chloride, and so on, the general tendency, so especially when you have a common anion system like AX, BX, these terms generally are negative. Sometimes they're positive, but usually they're negative, particularly when you have AX, BX. Most cases, in molten salts, these are negative, and as you saw, often they can be quite negative. Okay, so the AB second nearest neighbor bonds tend to be stronger than the AA. And you can also show this just from a Coulombic thing. If these are Coulombic interactions, which are given by simply the distance between the ions, if you take two ions of the same size, two other ions of the same size, and you make a bond with the two different ions, you end up with a negative energy. So these tend to be negative. Now, but let's say we go into the middle of the system. So we're now taking this term, and we're down somewhere around the middle here. in the middle of the square. Okay, now this term here is due to forming AB bonds, second nearest neighbor bonds. But because of your first nearest neighbor ordering, you don't have any. You don't have many AB bonds because there tends to be first nearest neighbor clustering. You have A X's and you have B Y's. So we have a whole bunch of AX clusters in which you have AA second nearest neighbor bonds, and you have a whole bunch of BY clusters in which you have BB second nearest neighbor bonds. You don't have very many AB second nearest neighbor bonds because of the first nearest neighbor ordering. Now, if you have an ideal mixture, if you don't have first nearest neighbor ordering, if your delta GX change is small, okay, then you don't have much first nearest neighbor ordering, and then this whole thing is correct. It makes sense. Okay, the probability. In this case, the probability in an ideal mixture, the probability of an A, B, second nearest neighbor bond separated by an X is YA, YB, YX. But in a non-ideal mixture where you have first nearest neighbor ordering, it's much less than that. You don't have very many AB bonds, so this term, which is due to the formation of second nearest neighbor AB bonds, is important here, but it's not important in the center because you don't have many second nearest neighbor AB bonds. Okay, so the first nearest neighbor ordering makes these negative terms less important in the center. Okay, and so it should bring it back up, and that's what happens. If we make this ideal assumption, we're getting that term too negative in the center. We want to have more positive deviations in the center, and the reason is these terms, these second nearest neighbor negative terms, must be made less important in the center. And we've tested this all out, and this is really what's going on. And this is not a small effect, as I showed you on the diagrams. So, how do we take this into account? And this was the subject of Desaros's thesis, so this was number 26. Okay, this, you're not responsible for the mathematics in here. I just want to show you how we take this into account mathematically. So this was the problem, too big the gaps here. You take this into account without taking that effect into account, and now it's okay near the edges, but it's too negative in the center, which is what you expect. You see, this, it'd be mainly, the biggest effect of this problem would be in the center, where you have the biggest short-range ordering AX. If you get out towards the side, then you still have quite a few A and B second nearest neighbors. But in the middle, that's where you have the least number, and that's where we're getting the biggest problem. Plus, we did a number of, you do a number of hypothetical systems. Take a bunch of systems and just make all the binaries ideal, so that, you know, all of these alpha terms are zero, and then you don't get that problem. It's when you start making the alpha terms negative that you start to get that problem. That's what's going on. Okay, so what Desaros did was, I'm not responsible for the math here, but you can look it over if you want. I found the equation somewhere. All right, this is the equation that Desaros was proposing. This is going back now to the equation here. G is XAXX, G naught AX, the same as before, minus T del S configurational. This term here was actually, this is like the Blander term. This is XAXX plus Y, and doesn't matter. This is this here. Then this term here he called them W, now we're calling them alpha. In the ideal mixture, the probability of an A, B, second nearest neighbor bond separated by an X is YA, YX, YB, simply the probability of finding an A on this site, a B on this site. This ABX bond is basically, you have an A on this site, you have an X here, and you have a B here. What's the probability of finding an A, B, second nearest neighbor separated by an X is simply, here we're using X's, but YA, YB, YX. And he said, well, no, the probability of finding an ABX bond is diminished by the Y. This is the Blander probability. This is the same thing as I used in the slide when I was doing the lambda term. This says the probability of an AX bond is XA, XX plus the variational parameter Y. Okay. So rather than XYA, so Y is your variational parameter in the Blander model, which gives you the deviation from ideal mixing in the first nearest neighbors. When Y is 0, you have a ideal mixing, just like on that slide 22. So if Y is 0, the probability of an ABX, this is alpha ABX, the probability of an ABX second nearest neighbor pair is XAXX times XB. But Y now, but he's changed this here. So this is the probability of he's trying to work out this term here, which is the probability of finding an A, B, separated by an X, taking into account the short range order. Okay, short range order being given by this variational parameter Y. Okay, so what is this then? And this is explained on the next page. Okay, for a second nearest neighbor interaction, the energy is now multiplied by the probability of finding such a grouping. So what is the probability of finding the grouping AXB? In a random mixture, it's simply XAXXXB. Okay, but in the taking into account the non-random mixing on the first nearest neighbors, the probability of an AX bond is the probability of finding an X here. Well, that's just simply XX times the conditional probability of finding an A here, given that there's an X beside it, times the conditional probability of finding a B here, given that there's an X here. Okay, so probability of an X. Now the conditional probability of finding an A here, given that there's an X here, is the probability of an AX bond, which is XAXX plus Y, divided by the probability that there's an X here. If Y is 0, this is simply XA. The conditional probability of finding a B here, okay, given that there's an X in the middle, is the probability of finding an XB bond, which is XBX or XBXY minus Y, divided by XX. So this is the probability now of finding an AX bond, taking into account the non-random, the short range order, first nearest neighbor short range order. So if Y is 0, you have no short range order. This reduces to the old equation, XA, But as you get short range order, if you work it out, you'll find this. The greater is Y, the smaller is this term. Okay, so that is what then goes back in here. Okay, so the probability of an AXB configuration, the probability of an AYB configuration, and so on. So the Y's, the little Y's, the variational parameter, which you sent that the GDY equals 0, must be included not only in the G naught terms, but also must be included in these terms here, and that takes account of this thing. I thought that was rather brilliant on his part, and now we ended up with things that were pretty damn close to the truth. But not quite, forget this one here. This is on all these diagrams, this is experimental. This is what you get without making the decimal correction. This was something that has to do with the pass and you can forget. And this is what you got with the decimal correction. So it's not perfect, but it's coming reasonably close now. An awful lot better than that. Just about the same at the ends, brings it up in the middle as you'd expected. This was the experimental without the decimal correction with it. This is the final version from his paper, experimental. Remember now, this is completely predicted from the binaries and the G naughts. There's no ternary terms in this. Considering the strength of the interactions, well, it's not too bloody bad. That one there. This is experimental. This is his. He actually still ended up with a little tiny gap here, but you can see it's pretty close. This one comes out perfectly, even better than it does with the blend. Okay, so we pretty well established that was that's what's going on. The reason I'm not having you memorize these equations is we're not using them now, because there's still one thing that's missing. And the thing that's missing is now we're taking into account first nearest neighbor ordering. So the quasi-chemical model is taken into account first nearest neighbors, anion, cation ordering. And it's taking into account, now the Desarel model is taking into account the effect of the first range ordering on the second nearest neighbor terms here. Okay. But it's assuming that in the binary systems you still have random mixing. Because this is still, in the binary system AX, BX, we're still assuming that the A's and the B's are randomly mixed on the cation sites. Whereas in fact, we do have second nearest neighbor short range ordering. in this system, the A's and the B's, if alpha is negative, this is now a single sublattice quasi-chemical model on the sub-AB, on the cation sublattice. Okay, and if you write it out this way, which Dessereau did, you're assuming that you have a random mixing on the AB, on the cation sublattice. But if this alpha is negative, then you simply have this reaction here. Sorry, the second nearest neighbors are ordered. The A's tend to be close to B's. You should be treating this as, in the binary system, you should not be treating this on the second nearest neighbor should not be treated as a random mixture, but as using the one sublattice quasi-chemical model to take into account the short range ordering on the second sublattice. Okay. So you would have AA, second nearest neighbors, plus BB, these are second nearest neighbors, all separated by x's here, form 2AXB second nearest neighbors, and the delta G for that is negative, so you tend to have second nearest neighbor short range ordering. On the same sublattice, the A's and B's tend to be nearest neighbors, as I showed you with the lithium chloride, magnesium chloride, cobalt chloride thing. And the Dessereau model doesn't take that into account, and that's the reason still that we're left with a small problem. And if these alphas become negative in the binary system, then the second nearest neighbor short range order must also be taken into account. So this Dessereau model accounts for the first nearest neighbor short range ordering, which is the most important because the first nearest neighbor bonds are stronger than the second nearest neighbor bonds. And it accounts for the effect of the short range order, first nearest neighbor short range order on the probability of finding these things, but it doesn't take into account. So you're in the Dessereau model, we're forced to treat every binary system using a polynomial model. We would like to treat the binary systems also using a quasi-chemical model, one sublattice. Okay, is that clear? All right. How do you do this though? Now, because the quasi-chemical model is a pair model, we're considering pairs, first nearest neighbor pairs or second nearest neighbor pairs. Okay, it's a cluster variation method in the pair approximation, if you like. And here we're talking about first nearest neighbor pairs, A's next to Y's, B's next to X's. Here we're talking about second nearest neighbor pairs. And you just can't put the whole thing together treating pairs, two different kinds of pairs, okay? What you have to do then is you have to couple these, and this was the final thing. We came up with then what is called the modified quasi-chemical model number 4. And now we're getting into the most... And this is number 28, modified quasi-chemical number 4. This is getting to pretty dense mathematics, but I will explain to you how this works. All right, two sublattice quadruplet approximation. This formed Patrice Chartrand's PhD thesis. For which, in case you don't know it, Bragg won the prize, Canadian Institute of Metallurgy Prize for the best PhD thesis in materials in Canada in 2000. I throw that in. Okay, so we talk about quadruplets. So we're now in the quasi-chemical model, but now we're going beyond the pair approximation into a quadruplet approximation. This is the only way really to couple. We have to couple the first nearest neighbor and the second nearest neighbor short range ordering. And I showed you in some of those things in the Dessereau paper that this was important even in the systems with monovalent ions, where all the examples in Dessereau's paper there were monovalent alkali halides. If you get into things like magnesium chloride, like the ones I showed you, cobalt chloride, cesium chloride, this becomes really crucial. I mean, without this, you just don't get quantitative results. I mean, they're qualitatively correct, but this is not the coupling of the first and second nearest short range order in these salt systems. And remember, salt systems are ionic systems, as are oxide slags and so on, so this also applies to oxide slags containing sulfur and the like. You really have to take into account this coupling if you want to get quantitative predictions. So it's not like a subtlety, it's important. So what we consider is we have your lattice, your two sublattices with your positive and negative ions on it. Okay, those are your two sublattices. Well, we want to take into account first nearest neighbor short range ordering, the probability that an AB will be AB nearest or AX nearest neighbor pair will be greater or less than the ideal, and second nearest neighbor short range. These are second nearest neighbors, but they might be ordered as well. So what we have to do is we have to consider quadruplets. And a quadruplet in this model contains 4 ions, 2 cations and 2 anions. Okay, so that quadruplet encompasses first nearest neighbor pairs, and it encompasses a cation and an anion second nearest neighbor pair. Okay, so here are some quadruplets up here. This is an AAXX or an A2X2 quadruplet, so this is what you get in pure AX only. Here you have an ABX2, so this is what we call a binary quadruplet. So this is AB but with the same X here. And this is a reciprocal quadruplet in which you have A, B, X, and Y. Of course, the thing can go up to higher. You can add C, D, E, and Z, W, and so on. But you still have these quadruplets. Okay, if you're in a binary system, let's say you're in the AX, BX binary system. If you're in the AX, BX binary system, then all the first nearest neighbor pairs are all AXs or BXs. So really, in a binary system, a quadruplet simply becomes a cation-cation pair. Here you have, let's say this is A, this is B, this is X, and this is X. Okay, in the binary system, all the quadruplets in the binary system, your quadruplets are either A2X2, B2X2, or ABX2. In other words, your quadruplets correspond to second nearest neighbor pair. So in the binary system, AX, BX, the quadruplet model simply reduces to the quasi-chemical pair model on the sublattice. These, you can forget the X's. Now you just have an A2X2 quadruplet is simply an AA second nearest neighbor pair. A B2X2 quadruplet is a BB second nearest neighbor pair, and an ABX2 quadruplet is an AB second nearest neighbor pair. So we might consider the quadruplet reaction A2X2 plus B2X2 forms 2B ABX2. That's your quadruplet interaction going from quadruplet exchange interaction. Remember, in the quasi-chemical pair model we had pair exchange reactions. Now we have quadruplet exchange reactions. So this is an A2X2 quadruplet, a B2X2 quadruplet ordering to form. Okay, but in the AX-BX binary system, an A2X2 quadruplet is simply the same as an AA second nearest neighbor pair. This is a BB second nearest neighbor pair, and this forms 2 AB second nearest neighbor pairs with X's. In other words, the quadruplet interaction, the quadruplet exchange in the binary common ion system reduces to the quasi-chemical pair model. So what I want is I want this model here to, in every binary system, AX, BX, I want this to reduce exactly to the binary second nearest neighbor thing. But now you see that taking into account quadruplets, we can take into account first nearest neighbor and second, and the coupling between first and second nearest neighbor short range ordering. We can have short range ordering because we have a whole bunch of different kinds of quadruplets now. Okay, in fact, in a system AX, BY, you have 1, 2, 3, 4, 5, 7, you have 9 kinds of quadruplets. You'll have if you go here from AX, BY, AY, BX, you have the quadruplets at the corner, which are like A2X2, B2Y2. You have the quadruplets, the binary quadruplets, this is like ABX2, BB, XY, B2, so you have quadruplets like X2B2, which contain 2 different anions, and then you have your reciprocal quadruplet in the middle, so you have actually 9. Okay, so the ordering between these 3 quadruplets takes into account second range ordering in this system, like I did here, and then you can get second nearest neighbor ordering in this subsystem, and this subsystem. on the respective sublattices. Or if you take this quadruplet plus this quadruplet gives you this plus this, and that's your exchange reaction. Okay, so this plus this plus this plus this plus this minus this is your exchange reaction. So that's your first nearest neighbor ordering. This plus this gives you this is your second nearest neighbor ordering. The reciprocal quadruplet is a bonus. Okay. So by doing this quadruplet thing and trying to keep the whole thing coordinated, we can, what we want now is we want a model that, and what this has to do is it has to reduce to the, all the other models. In the binary systems, it has to reduce to the modified quasi-chemical model on one sublattice. And in the reciprocal system, it should basically reduce to the, well, the Desiro model, but with the additional bonuses now that you're taking the second nearest neighbors into account. And it does that. Plus, just as before, you can do anything you want. Remember before, if I said if you had some binary subsystem, as we did with the quasi-chemical model in the ternary systems, you can mix models. If you're having a multi-component system and a binary system has been fitted with a polynomial, and another has been fitted with the quasi-chemical model, you can mix the two. You can do the same thing here. You can pick all the previous models are in this model. And by making certain assumptions, you can force it to to be ideal if you want. You can do anything you want with the whole thing. So, and the Z's, all the coordination numbers have to be the same. As you remember, we have to have a second, we wanted to have in a binary system AB, you got ZAA, you've got your ZBB, you've got your ZA in the AB, you've got your ZB, all that business. Everything we've talked about has to sort of go into this model. All other models are are special cases of the big model here. You can suppress ordering on the second nearest neighbor. If you actually suppress ordering on the second nearest neighbor lattice, then you end up with the Desiro model and so on. So there's no way that I can possibly go through this mathematics, nor maybe is it completely necessary for you to understand all. I'm certainly not going to ask you to reproduce this mathematics on any type of an exam. Okay, just however that the entire thing reduces, we have very general equations, but if you apply these general equations to specific subsystems, you'll find they reduce exactly to what we had before. Okay, here, so you have coordination numbers. You have coordination numbers for the for the quadruplets, and these coordination numbers for the quadruplets in a binary system reduced to the second nearest neighbor coordination numbers that you used in the modified quasi-chemical model for that subsystem. Okay, and I could, well, if I wanted to show you how to do the whole thing with all the entries into FactSage and how everything, that would take another 3 or so weeks for the course. You're going to find this out as you go along, so I'm going to leave that up to you. And you want to read this paper if you see how the whole thing works, and it's not easygoing. But the whole point is there's nothing really new here apart from the concept that the quadruplets permit you to take into account the first and second nearest neighbor orders simultaneously with the coupling between them, and that the thing reduces to all the other models. So you fit up, what you do is, and if you're going to analyze, if you're going to do an optimization of if you're optimizing a big, and it takes all the equivalent fraction things that I talked about are taken into account in the whole thing. So if you're going to analyze a system, sodium, potassium, calcium, magnesium, mixed with, say, fluorine, chlorine, sulfur, oxygen, whatever, you then go through every binary system, AX, B, all the binary systems, AX, BX, are all fitted with the one sublattice quasi-chemical model, using equivalent fractions if you want to, or if you don't want, if you want to fit it with a polynomial, you can bring in all the Z's, so you do all the binaries. Then all the ternary common ion systems, AX, BX, CX, or it could be CX2, whatever, they're all fitted again using the one sublattice quasi-chemical model for ternary systems exactly as we did before. So eventually then you fit up every subsystem A, B, C, D So eventually you're going to end up with a subsystem: sodium, potassium, calcium, magnesium, fluorine on the cation sublattice, and then the same thing with the subsystem for sulfur. Then you do then you bring the whole thing together into the reciprocal system using this. And this will give you an approximation. Then, and also these reciprocal Gibbs energy of the reciprocal quadruplet. There's a whole business at the end here where the Gibbs energy of the reciprocal so your ternary, okay, you have two kinds of ternary terms. All these were you have binary terms, which are the same as binary. The ternary terms in the common ion system are exactly the same as the ternary terms that we talked about in the modified quasi-chemical model number 2 in the ternary systems. Same notation, same numerical values, whatever. Okay, so all the subsystems can be fitted with this model. Once you have all the subsystems together, now you have the Gibbs energies for once you have fitted the subsystems, you'll have the Gibbs energies for the quadruplets at the corners, and you'll have the Gibbs energies for the quadruplets, for the binary quadruplets. The model will automatically give you the Gibbs energy of the reciprocal quadruplet as an average of these 4 here. But then later on you can put that in as an adjustable parameter if you wish. Okay, but first of all, if you fit up all the common ion systems, A, B, C, D, E, X, A, B, C, D, Y, all the common ion multi-component systems, you put them all together, the Gibbs energy of the reciprocal system will be automatically estimated for you, and when all the coupling and everything taken into account, and you'll get the first cut for the phase diagram. You can then add reciprocal adjustable parameters if you wish. Okay, you can adjust the Gibbs energy of this reciprocal pair here, reciprocal quadruplet if you want, from the default value, which is calculated for you. And there's other possibilities in here of altering of adding additional, what we call reciprocal ternary terms. Okay, you have binary terms from the AX, BX binary systems. These are binary second nearest neighbor terms. You have ternary second nearest neighbor terms from fitting the ternary subsystems with common ions. Of course, you need your G-naughts of your pure materials, just as you do in any reciprocal model, which are some of the most important things. So you have ternary common ions, ternary second nearest neighbor terms. Then these are your ternary first nearest neighbor terms, or these reciprocal terms, which are estimated for you, and you can fiddle around with them if you wish. It reduces to every other model. This is now called, in fact, Sage Model 98, which everyone humorously calls GUTS, the Grand Unified Theory of Solutions. We also had in the past a Model 99. What's the difference between Model 99 and Model 98? It has to do with, we made a small, well, I wouldn't call it an error. Mathematically it's not an error. The entropy expression is a little, without a better entropy expression, which is, this is something you don't have to worry an awful lot about, but for those who want to know, what the hell is it? The entropy expression has changed a little bit because oh. What is that entropy expression? Let's see it. All right, here we go. All right, this entropy expression here, section D, equation 39. You're not responsible for this. You might just be interested in how this thing works, because this is what the cluster variation method works this way. Remember in the binary quasi-chemical model, or in the quasi-chemical model, what we did is we first of all distributed the pairs. You first of all distribute the pairs, minus RZ, XAA, log XAA, plus XBB, log XBB, etc. Then you say, well, that overcounts the pairs. So you divide by the number of pairs in an ideal solution, and then here you add on the xa log xa plus xb log xb. Okay, so you distribute the pairs, divide by the number of pairs in each thing, and the number of pairs in an ideal mixture, and then you put on the ideal. Now in the quadruplets you go one step further. You first of all distribute your quadruplets. So this is the number of quadruplets, number of A2x2 quadruplets times log number of quadruplets, number of ABx2 quadruplets. So it's number of quadruplets sigma number of quadruplets log number of quadruplets. Then you have to divide by, for each quadruplet you have to divide by what would be the mole fraction of that quadruplet in a solution in which the pairs were randomly mixed. In which the quadruplets were randomly mixed, but not the pairs. Sorry. So here, this is the mole fraction of the pairs, and then this is the mole fraction of the pairs in a solution in which the pairs are randomly mixed. This then is the mole fraction of the quadruplets. You're distributing the quadruplets on quadruplet sites. Then you're dividing by the number of each kind of quadruplet in a solution in which the quadruplets are randomly mixed, but not the pairs. Then you're putting in this term here, distributing the pairs now randomly over the pair sites, dividing by the number of pairs in an ideal solution, and then you go back to the point approximation. So you distribute the quadruplets, divide by the ideal number of quadruplets. So you're going one more step. So you're distributing the quadruplets, RZR log x of one kind of quadruplet, log x of that quadruplet, divide by the number of quadruplets in a random mixture of quadruplets in terms of the number of pairs. Then you take the pairs, distribute them over pair sites, divide by the number of pairs in an ideal solution, and then you distribute the atoms over the points. That's the cluster variation method. And there have been cluster variation methods, similar things in which you went even a step higher. You might have groups of 8. You distribute the groups of 8, then the groups of 4, then the groups of 2, you work your way down. We discovered a few years after doing this that this denominator here wasn't quite right. This is a statistical thing, the number of quadruplets in a solution in which the quadruplets are randomly mixed but not the pairs. And that all came up from here, which you can read, and if you read this and think about what it turns out to be, we decided about 3 years ago this wasn't quite right, so we changed a little bit the denominators here. So model 99 is the old one, model 98 is the one with a slightly increased entropy expression. It doesn't make much difference except in the middle of systems in which you have quite a large exchange gives energy, and then it makes some difference. So 98 is better than 99. There's no difference in the way you treat it. You just why don't we just change everything to that? It was because there were some things that were fitted with the model 99 that fit a bit better, and we didn't want to have to refit them. But from now on, in anything new, you use model 98, which is a bit better. So that's this. You're not responsible for all the mathematics in this for sure, but this is the final answer, and this encompasses everything else. Okay, and this better entropy expression, we've written that up somewhere, but I haven't got a paper on it yet for you. The new one just has a little bit better thing here. You want to read about it. I'm trying to think, okay, those who like statistical mechanics can read this business here. The probability of an A, B, X, Y quadruplet in an ideal solution of, and try to see where you think we went wrong in that. It's pretty subtle, but it doesn't make a big difference between 98 and 99, but 98 is the preferred one. Okay, the point though is that this model reduces to all the previous models for one sublattice with all the z's with the same numerical values. The z's of the coordination numbers of the quadruplets reduced to the z's of the pairs in the subsystems, so you can use exactly the same parameters. And we've tried to make the entry reasonably simple. Actually, when you do the entry into the database, it's kind of simpler than this. Now, if you take this model 99 for a slag that has only oxides, so you're taking a slag such as calcium, magnesia, silica, which has only oxides, no sulfur, sulfate, or anything. For the slags, calcium, magnesia, silica, aluminum, we're using the one sublattice quasi-chemical model. Okay? But we could still write it in model 98 with all the anion sites occupied by oxygen, and the whole thing reduces back to, okay, so model 3, in fact, stage model 3 is the one sublattice quasi-chemical model. Model 3 is your one sublattice quasi-chemical model, and that was used in the past for the slags. Okay, this has now been converted into model 99 by Sergei Dektorov. It's exactly the same model, nothing's changed. He's just put it into the model 99, putting only oxygen ions on the on the anion sites. Okay, so you'll see the entry is the same. Model 99 is this. Model 3 is like model 99, except that there's only one anion necessarily. You just ignore the anions. In model 3, you only talk about mixing the metals on the metal sites, and you forget about mixing the oxygens on the oxygen sites because there are only oxygens there. If you take this model and you fix all the ratios of the ZA to ZB constant, so the ratio of the number of sites on sublattices are constant, and you fit every binary system up using a polynomial model, then this reduces exactly to the compound energy formalism. Okay, however, this is limited to two sublattices. Okay, model 98 and 99 can reduce to the compound energy formalism, but only for a two sublattice model. Because this is a two sublattice model necessarily. Okay, if we go to greater than two sublattices in fact stage, basically at the moment we can't use the quasi-chemical model. For more than two sublattices, we're stuck with the compound energy formalism, which has its own model number. Actually, if you're using the compound energy formalism for two sublattices, it's easier to use, I think it's called model 20 or something, than to use this simply because the entry is simpler. Here you have to put a whole lot of default values in model 21, all the defaults are taken care of for you. Model 21, 20 or the 15 or whatever it's called, the compound energy formalism doesn't require you to put in any Z's because they're fixed. So, for example, so you just don't have to make some. But remember, these only work for two sublattices. More than two sublattices, for the moment, we're stuck with polynomial model. We've never tried to extend quasi-chemical model beyond two sublattices. What you should do if you are doing, I would highly suggest this to you for not for this course, but for your work. If you're dealing with slags, I think a lot of you are dealing with slags, okay? You're using model 99 or model 3? Are you fitting things up with in-house group using model 99 now, I guess? Okay. You could just try for fun as taking a system with, say, a ternary system with model 3, CaO, MgO, silica. Take the model 3 for that, put the parameters in for that on the quasi-chemical model, then enter the same parameters into model 99 for the same system with a different entry. Just make sure you really understand the correlation between the 1 and 2 sublattice model, because model 3 will only ask you for the second nearest neighbor terms for the AX, BX, CX system. Put them in model 3, then do the same entry in model 99 and just check at one point to be sure you've got the same thermodynamic properties calculated. Same phase diagram. Might be a nice exercise to try. Alright, and then show you. Yeah.
So if a cation has multiple valency, so are we going to means are they to be considered as different cations?
Oh yeah, they're different cation. Fe2 plus and Fe3 plus are totally different. Now it's so yeah. If you're treating a system like take a simple system, you're treating the system MgO, FeO, Fe2O3, one phase, the slag. You treat these as three separate components. Now, that doesn't mean you can't be anywhere at a given oxygen pressure. You're going to follow a certain. Okay, the solution will then the ratio FeO to Fe2O3 is fixed by the oxygen pressure. You can't just put yourself anywhere in the system you want. Okay, fix the oxygen pressure, you're going to follow a certain line, but that's done by faxing. But it's treated, yeah, they're treated as separate items. And it is it's a ternary system. Okay, and then, so this is the then lithium, sodium, potassium, magnesium, calcium, fluorine, chlorine reciprocal system using the modified quasi-chemical model. This was from the final paper from Patrice's thesis, and you can see here now how this goes on. If you read this paper number 29, you'll see how the experimental and calculated diagrams are agreeing with you. This is the experimental diagram, this is the calculated diagram. And no ternary parameters, no reciprocal ternary parameters are used here. Okay, we analyze all the binary, well here there's just binary, there's no ternary common ion systems, the G-naughts, and predictions are being made, and you see now we're getting quantitative, and these are across the join, going across the join, these are the liquidus points, and some, well, that's a different system, I guess, but so a whole lot of systems were done here, and you can check it out. But I mean, it's giving quantitative predictions. And I think for the most part, we didn't need to use any reciprocal, these are liquidus points across different sections comparing experimental and calculated. It works, we're getting quantitative fits. Systems. Now this system is a pretty good test. The magnesium and calcium systems with chlorine are quite non-ideal in the binary systems. Probably if we'd gone on to even bigger ions, rubidium and cesium, and bigger ion and smaller ions here, charged, then I don't think we would get quite such perfect quantitative fits, but then we can add the reciprocal term. But anyway, I felt really when we did this that we now understand these molten salt systems. Basically, this is what's going on. The physical model is pretty much correct. And this has been used for slags. Most slags that you're dealing with in fact, Sage, have only oxygen as the only negative ion, so it's lots of metal oxides, silica, calcium, magnesium, and so on. So it's the one sublattice model. There was an old model in fact, Sage, which I don't think I'll go into it, but Inho knows all about it because he's done work on it, which was a model where we made approximations for adding other cations, like slags containing small amounts of sulfur, sulfate, water, hydroxide ions, fluoride ions, and so on. This is called the capacity model, sulfide capacity model. And this is not based upon the different sublattices. This is maybe I can talk about that a little bit later in this course. It's a simple model that we did for dilute solutions. Has nothing to do with this. It still doesn't consider. It's still based. It's the one sublattice model for the oxides in which we added some approximate terms to explain the solubility of small amounts of sulfur, hydroxide, fluoride, and so on, and slags. And that, in fact, is what you're using. If you go to FactSage now, you have slag A, slag B, slag C, slag D. You've all seen that, I think. No, you don't know that. Okay, you see the slag C contains sulfate, slag D contains fluoride, slag C. All of these use this capacity model. They're not using the modified quasi-chemical model. It's an approximate thing, and they're only for dilute solutions. With one exception, though, slag A contains sulfur, S minus minus, not as sulfate, but as sulfide. So under reducing conditions, you can get sulfur in slags. As sulfur, S minus minus ions. I'll talk later in the course about slags and these things in detail, but this is just so you know what all the models are. If in a slag, if you have sulfate, that's sulfur in the slag under oxidizing conditions. The sulfur goes into sulfate ions. If you look at slag B, I think it is, the sulfate ions are treated in dilute solution using this approximate model. If you're under reducing conditions, then you will get sulfide ions. And sulfide ions are treated now as part of slag A using model 98 and doing it the right way. That is, the sulfur and the oxygen are considered as two separate anion. And so now we have quadruplets. We have a quadruplet, for example, could be a silicon, calcium, a sulfur, and an oxygen. Okay, and this was done by Yunbei Kang. That's his postdoc. And now that is the only, in the slags, the only place where we actually are using modified quasi-chemical model with the coupling, with the proper coupling between the first and second nearest neighbors, is in the slags with sulfide. And I put on here, well, it isn't here. Okay. It's on the server. I'll show it to you tomorrow. Number 48. Number 48 is the recent paper with Yunbei in which we did all the slags. And you can see how nicely the model fits there too. I'll talk about that a little bit tomorrow. So with just a little talk about that tomorrow, that pretty well completes. This is the worst the math is going to be. Now, from now on, I'm going to talk about, for the rest of the course, I'm going to talk about applying some of these models to specific systems, non-stoichiometric compounds, ceramic systems like spinels, molten salt, slags, so on. So it's going to be, say, more chemistry from now on than mathematics of modeling. But this is as far as we've ever gone in the mathematics of modeling. I have no intention in my life to make it any worse than this, although I have been tempted to do so. But I'll talk a little bit about well, there are models that go further than this, and I think my philosophy in a model is you can take it too far, and then all you're doing is fiddling around. You got so many adjustable parameters, you can fit anything, and you're not predicting anything, and you're taking the whole thing too literally beyond a certain point. However, I think up to this point, we're not taking it too literally. The success we get with fitting these things indicates that, well, for instance, this business here about, I mean, is this just mathematical nonsense? I don't think it is. I mean, I'm sure it isn't. The first nearest neighbor ordering is affecting the second nearest neighbor, and this is the fundamental reason why it's doing it. But you don't want to start taking this too far. And when you start to take, well, this is my own personal thing, when you take, you'll see the cluster variation method in which you'll take a face-centered cubic lattice, and then they'll take the geometry of the lattice, and then you'll start to put hexagons and tetrahedrons and octahedrons and see how many ways they fit together, and you come up with huge. I don't think there's reality to that. Well, I'll talk about that a bit later. I don't think you can take this kind of a model can't be taken too much further than this without getting into the point of so many parameters that you really, are these extra parameters mean anything physically, or are they just adjustable parameters? You might just as well add a couple of polynomial terms. And in any case, if you have so many adjustable parameters, if you have a system with 30 adjustable parameters and you've only got 20 data points, you can't find the bloody parameters anyway. So, and you don't want to get any more. You really don't want to get any more mathematically complicated than that. Okay, so tomorrow at 10 o'clock, and then not next Tuesday. I'm considering having a final quiz, a second quiz. You said you want one more. A second quiz in, say, the second last week, so that would be like the 17th, I think, the Wednesday. That's the second. Well, no, sorry. Well, next week is the 11th is the, what's today? Second. Today's the second, right? Yeah, so the 9th would be the next week, and 7th, 16th. On the Wednesday the 16th, we could have a...
On 14th we have a exam, another course.
Well, we're going to have a final exam during the exam week, which is, the 7th or 8th of December. We could have only a final exam. What I would like to do is have a second quiz, which is more on this mathematical stuff, and then the final exam just will cover everything. Even though the final quiz is only 2 weeks before the final exam, there's not much material after the final quiz, but it gives you a chance to redeem yourselves afterwards. I've also a couple of times in the past, we had the first 2 quizzes, and then if you did okay on those first 2 quizzes, I said you could be exempted from the final exam. But if you haven't done well, then you can take the final. The final exam is optional. Let's put it that way. I'm not sure I'll do that this year, but if you make the final exam optional, then that means if you've done well, just don't do the final exam. If you haven't done well, then you can give it a... See if maybe we can do that. We'll see. Anyway, we'll talk about it tomorrow. Okay, I promise no more hairy mathematics beyond this. We've finished now. I stopped it. I just stopped it.